All right. So perhaps I'll begin with the introduction. So it is my pleasure to welcome you and welcome the speaker of this lecture to this public event, public lecture, which is actually a part of a series of lectures sponsored by the Institute of Physics, IOP, and hosted by the physics team at the University of Wolverhampton. So today we have a special speaker, special guest, Professor Jacopo Bertolotti, who is Associate Professor at the University of Exeter. So he is originally from Florence, Italy, where he obtained his degree in physics in 2004, and then his PhD in 2009 on light transport in scattering media, and so he contributed to the development of random lasers. Correct me if I'm wrong, Professor Bertolotti.
I worked also on random laser. It was never the core of my research. I worked on different things, undersoul localization and anomalous transport of light when I was doing my PhD. So random laser was a part of it, but the real specialists are other.
All right. So it is anyway related. And well, I just wanted to say that it is related to the field of random lasers somehow, and say that, well, you can learn from it that physicists love lasers so much that, well, they invented random lasers on top of regular ones. Okay, so I'm not sure if there is going to be a animation on that, if then I'll leave it for you to imagine what it looks like and Google it later. So then, after his PhD, he did a couple of postdocs at the University of Twente, Netherlands, and then in Paris, France. And after that, finally, well, in the year 2013, he became a lecturer at the University of Exeter in UK, where he is now, well, associate professor, working on imaging in scattering and turbo media. So as you see from here, well, today's speaker, well, and physicists in general like to work with turbid and turbid, let's say, unclear matters. But in the case of today's speaker, literally, so he is working on turbid media, and his work is to somehow elucidate them. Right. And I just wanted to say that, well, from naturally all researchers and physicists in particular have to illustrate their works and their ideas, their well, concepts somehow. But today's speaker took it to the next level, and he made it a hobby, an art, and well, his passion, I suppose. So I hope you anticipate his talk already. On top of that, well, of course, he's still at his say early stage of his career, which is extremely successful, and well, it finds the reflection in the fact that he obtained he was awarded with a Mosley Medal for early career developments in experimental physics in 2016. So perhaps the last comment is that he actually insisted that, well, due to the interactive nature of his talk, we have to allow questions during the talk. And the way we are going to do it is probably by the use of chat. So you can type your questions in the chat attached to this Zoom meeting, and I will interrupt, I will use my position to interrupt the speaker and ask the questions. Right, so without further ado, please, Jacopo, the screen is yours.
Thank you very much for the introduction. Thank you very much for inviting me to talk today. It's a very strange talk, very strange topic to talk about. All scientists are very much used to talk about their own research, their own results, or to give lectures and things like that. And I'm very used to that too. Today is going to be different because I'm going to talk about animations about physics. And therefore, I will start with a couple of disclaimers there. I'm just a hobbyist. I'm not a specialist. There are people that study how to best convey scientific ideas through various media. And there is a whole field about it. I'm not a specialist there. I never really studied how to make scientific animation. It's just a hobby. I just started and I like it, and people seem to like my animations, so I kept making them, and that's it. So I'm not even particularly good at coding, to be fully honest. A lot of people seem to assume, given that I make this animation, that I'm some sort of computer wizard. I'm not really. I know the basic of coding, of course. I can put together a for loop or things like that, but I'm not a specialist at coding. I do my best there, but one of the main messages is that you don't actually need to be super good at coding to make this thing. And last disclaimer before I start is that due to the previous 2 points, everything I'm going to say is just my own personal opinion and how I see the thing. Don't assume that these are rules or some kind of very illuminated set of things to do or not to do that you have to follow. This is just my view on this and the way I see how to best do animations and stuff like that. Okay, the outline of this talk is going to be very simple. I will start by talking about why you should make an animation about physics. Then I will talk about how you make an animation about physics. And then I will conclude the talk and have some closing thought about the topic. And let's start by why anyone should animate physics. And this is a very wide question because there are a lot of different possible goals that you might want to achieve with your animations. And I've seen people good at different one of them. Very few people are good at all of them. And your goal is going to dictate very much how you are going to do your animations. Now, a first possible reason to do animation is to make art. And there are out there people that do really beautiful stuff there. In this case, the goal is not really to have something that is physically exact or that is a result of a good simulation or anything. It's more about eliciting a feeling, create a mood or something. It's possible. There are people extremely good at it. I'm not particularly good at art, so I never even tried that very much. A possible goal, and that's something that a lot of people actually do, is to make small animation to wake up people during your talk. You have your 15 minutes talk, you are discussing your results, And unless you are extremely good at talking, or you have a very good slot in the day during the conference, after a few minutes, people will start drifting off and dozing out. And the small animation, it's usually a good way of waking them up. People have used that to very good effects. There are a lot of very good talk out there where, let's say that there is the experimental setup that is nicely animated that help explaining what's happening there. I have seen people going a bit overboard with that and have talks that were nothing else than a long sequence of animations, which is fine. They might get a bit tiring after a while. Similar, but slightly different, is to wake up students during your lecture. Once again, if you are a university lecturer like me, you have your 1 hour lecture, and you all know that students, sooner or later, they are going to lose concentration. An animation here and there is a good way of picking their attention again, so they stop thinking about whatever else, they stop checking their mobile phones, and they just check what's happening on the screen, and therefore, what are you talking about? Some will go back checking their phone after 2 seconds. Some will start paying attention again because they realize that actually what they're seeing is interesting. An animation might help explaining a concept, and this is mostly the way I see animations, and it is essentially the leitmotif of all the animation that I will show you today, and the way that I'm going to talk about animations today. I will talk more about this later, but in general, an animation can be a very useful tool to make clear what you're talking about. There is also a last possible reason to do an animation. This is for pure fun. And yeah, and I don't mean fun for the people looking at it. If people looking at it are having fun, you're probably going back somewhere in the art department here. By fun here, I mean fun for the creator. If you might be doing an animation just because it's fun to do it and you want to see the result. So let's go back and talk a bit more about the idea that we want to use an animation to explain something. And let's look at it from an example. Now, we are all used to textbooks. Textbooks are a great way of sharing ideas and science since a very long time. And people have used images in books since very early. Why? Because they are useful. It's very easy to explain with an image something that is very hard to explain with words or equations. Now, an image, it's unlikely that we'll be able to bring you all the way through, but it can clarify things. Now, this is an example of an image, and there's actually a good one. You might, if you did a physics degree, you might have seen either this or a very similar one. This image is about quantum tunneling. Quantum tunneling is this strange property of quantum mechanics that you might have a particle arriving on an obstacle and it can just pass through the obstacle, even though it shouldn't have enough energy to overcome the obstacle itself. This is from a standard quantum mechanics book from Griffiths, and it's a good image. You have your particle arriving is a plane wave, so sinusoidal, technically complex exponential, but if you want to plot it, you plot a sinusoidal. Then here is the start of the barrier, and it shows that inside the barrier, the wave function is going to be a decay exponential. Everything here is smooth, so it's telling you that the wave function is going to be continuous and differentiable there. Also at the exit of the barrier, the exponential has gone down, but not to zero. Therefore, there is still a small wave going out, which is a small amount of probability there. Is this a good image? Yes, it is. And it explains exactly what's happening in the way that you also do the calculation. If you do the calculation about quantum tunneling, you do it, first of all, in the frequency domain, meaning that you look at it at one particular frequency, because it makes life easy. You have only one sinusoidal here. You can join this function in a smooth way so that you find out all the coefficients that you don't know a priori. You fix your boundary conditions here and here. And then you get out at that particular frequency how much of the probability of the wave function is going through. This is great. It works very well. It's hiding a lot of information. And the information is there, is implicitly there, both in the image and in all the equations that you have to solve to go through the whole thing. The equations are going to be in the textbook. You go through them as a student. But the time behavior is somehow implicit in there. It's never really shown. Why it's not shown? Because it's difficult to show the time behavior of something on a printed page. Printed pages are great, but they are static. Now, what can we see if we just look at exactly the same thing, but now in the time domain? Now, here is an animation of the time domain. You have a pulse. This is your particle arriving. It's a superposition of a lot of single frequencies, so it's a superposition of a lot of this thing. Create a pulse that tells you where is the high probability for your particle to be. It's moving because your particle is moving. It's arriving at the barrier. This high red thing is my barrier, and some of it is passing, and some of it is reflected. But then there are things that are not obvious from here. For instance, there is all these fringes, all these spikes created. What are they? Well, these are the interference between the waves that go in one direction, the waves that go in the other direction. Remember, quantum mechanics, particles behave like waves, so they interfere. And that is exactly that interference. You can also see that the probability is usually zero. This is a zoom of what's happening near the boundary. And you can see this exponential that is essentially sitting at zero and grows up. And then it goes back down back again and creates this other small copy of the pulse that is actually representing the small probability to get transmitted. All of this is implicit in the equations, but it's not obvious unless you have spent a huge amount of time staring at the equations. It's not obvious that any of this is what's happening, because the only thing that you are seeing is what's happening at a single frequency. Time domain, sometimes it's different. It contains different informations, and an animation is ideally suited to give you that information. Since we are talking about quantum mechanics, other example of things that you might see in the equations, but is not obvious. Here, upstairs, here is another standard textbook problem. You have the rectangular potential well. You have your particle, it's the pulse that is coming in from the left. And then you have the potential is flat everywhere except that there's a dip. And standard problem, although there is a dip, you have this, given that the particle behave like a wave, you have reflections from these edges, from any discontinuity. You get reflected back, and part of this pass-through, you see the fringes created here again, interference between the waves that are still going left to right and the waves that are reflected that go right to left. And then you get these two small bumps that are reflected here, reflected here. There are technically tinier bumps of things that get reflected forth and back, but they are so small that you don't see them. Now, you might ask, and somebody did, not me, but somebody did, what happens if I change this shape? There is any shape that don't create any reflection? The answer is yes. There is this shape that's called the Posteller potential that don't create any reflection. So what does it do? You can make the calculation. It's not exceptionally difficult. And what you find is the reflection coefficient is 0, which tells you that there are no reflection, but it doesn't tell you what's happening there when you send your particle there. And the particle, the probability function that represents the particle in quantum mechanics is not just passing through. You can see that it's deformed there. And then everything just interfere correctly so that the pulse just propagate through. Again, example about quantum mechanics, you have probably all heard about uncertainty principle. Uncertainty principle in quantum mechanics tells you that if you know very well where your particle is, you have a very large uncertainty on the momentum, so the where the particle is going next, which means that if you start very narrow, you're going to broaden up very quickly because I know in this very moment where the particle is, but I know nothing about its velocity, its momentum. Therefore, at a later time, I know very little where it is. And it's not usually immediately appreciated out of the equation, although, again, the information is implicitly there, hidden inside the equations. That actually, if you start very narrow, you broaden very quickly. But if you don't start very narrow, if you start already decently broad, if you don't know very well where the particle is, but you also don't know very well what is the velocity, but you know a bit of both, on the long term, you know much better where the particle is going to be. So sometimes in quantum mechanics, measuring something too well is not great. You know very well what's happening now, but you might not know very well what's happening later if you measure your position too well. But again, this is implicit in the uncertainty principle. Is written in every textbook, but unless somebody shows you what's happening explicitly, it's not something that you will immediately think about. Now, just another couple of examples of this, and these are about optics. I do optics, I like optics, so I'm afraid that you will have to endure a few examples about optics. And these are a couple of examples that are usually not really trivial. The first one is what is called the GUI phase. If you have your light and you focus it, and you look at the phase profile of your light, if you make the calculation, you find out that there is a weird term, an arctangent phase term, and that's in textbook, they just say, oh, this is called the GUI phase. Essentially what it means is that when you go through your focus, there is an extra pi phase shift over your focus. And again, it's there in the equation. You can see it if you just simulate your focus. This is a very tight focus just to make everything nice and visible. And you compare the phase, these colors are the phase front of what's happening there. And you compare it with a plane wave that is going there. At the beginning, they are all in phase. You can see all the colors are nice and in phase. Then something is happening around the focus. Things get shifted a bit. It's a bit, the upper one is a bit delayed. And then once you go back, they are now going again at the same speed, propagating at the same speed, but pi phase shifted. This helps especially with students. You show them this, and it's a bit more clear what these represent. The phases coming in are propagating at the same velocity. The phase going out are propagating at the same velocity, but just around the focus, the phase around the focus is propagating a bit slower. So you get this phase shift. This is another example. This is surface plasma polariton, sometimes called the plasmon. And again, you can make all the calculations. It's not particularly difficult what this is. This is a bound electromagnetic mode between a metal and the dielectric. You get the surface, you get, for instance, a metal surface in air. And there are most of the electromagnetic field that are bound to that surface, and they propagate. And these are often called plasmons or surface plasma polaritons, you can calculate what the electric field is doing there, but it's not immediately obvious what that means. How does it look like? And you can just plot them. And what you get is, well, the field is extend a lot more in the dielectric than in the metal, which is pretty clear from the equation too. But the fact that the field seems to be rotating around is implicitly there, but it's not obvious at all if you look at the equations. It's just one of those information that you have to sort of tease out from the equations. So animations are good if you want to show what things do in time. That's pretty obvious. Time evolution is not something that is easy to show with a still image like the one that you have in textbook. But if you make an animation, it's natural to show things in the time domain. Now, this is not the only case where you might want to use an animation. Other cases include where you want to sweep through parameters. And this is when you have still images, this can be done by making several images where the parameter go from one value to another value to another value. And that works. Sometimes it's just easier to show where the parameter is swept continuously. Let's go back to quantum mechanics. We have seen what's happening in for the quantum tunneling, but if you try to make the same static image, the same one that was in the textbook, but for two barriers, not just one barrier, you have two, and you change the distance between the two barriers, this is known as resonant tunneling. There are some distances where you have a resonance in between the two. The wave that is propagating in, reflected back, and reflected back is just resonant. In this case, you have a lot more transmission that you will expect. You can actually get transmission 1, even though you are tunneling twice through barriers that technically you wouldn't have enough energy to go through. But if you are resonant, you get a transmission that is exactly 1. Again, you can do the calculation. It's not exceedingly difficult, once again. And you can plot several of these at different distances. But if you just swipe it, there are things that might not be completely obvious. For instance, if you look at the blue line is the real part of the wave function. Wave function is complex. You have to decide if you are plotting absolute value, real part, imaginary part, or something like that. If you look at these, you might notice that every time that you go through a resonance, there is actually phase shift. Everything seems to whoop and go back a little bit. There is just a phase shift there. You know from the equation that there should be a phase shift. How does the phase shift look like? This is how the phase shift look like. The whole thing just make whoop and go back a little bit. Other case, and this I admit, I made originally this animation mostly for myself. There is this thing called the covariant contravariant components of vectors. If you're not really into linear algebra, forget about it. It's just how do I represent this vector when my bases, these two vectors, are not orthogonal anymore. We are very much used to think in terms of orthogonal bases. So I have my x and my y, they are orthogonal. If they are not orthogonal anymore, and this happens a lot in relativity, then you have two choices. You can have the projection that is always with a line perpendicular to both of them, or you can have the projection that is always parallel to both of them. And these are choices. Both are extremely useful, and usually you want both of them. They represent different ways of representing your vectors, and you want both of them. But they are different choices, and that's how they look like. When you make the same two vector represent basis vector at different angles, this is how the covariant and contravariant component change. Or sometimes you just want to be a bit more memorable. Sometimes sometimes you just want to wake up a bit your audience. So you want something that is relatively straightforward. You just want to be a bit memorable. This is a Fourier series. Fourier series, you go to the textbook, it's any signal that is periodic, I can approximate it like the sum of sinusoidals. And usually the example that are there are the typical example is the sawtooth, the triangular shape. Because you can do it pen and paper, you can actually solve that pen and paper, and it's a nice exercise for students. But you can get a lot more complicated. I mean, you can sum sinusoidals and get the Batman logo. Periodic, because the Fourier series only work with periodic things. But if you take the Batman logo and you patch it periodically, you need two of them because, of course, the Batman logo have an upper part and the lower part. And these are two separate functions that you want to approximate. So you have two sets of sinusoidal going in at the increasingly high frequency. And if you sum enough of them, you just keep getting better and better your Batman logo there. This is a bit more technical. You have a Gaussian random distribution. So you select random number from a Gaussian distribution. The radial distribution is known as the Rayleigh distribution. And you can imagine it to be, I get my random distribution, then I just swipe around with my radius to collect all of them. And then I just count how many there are. And I get this distribution that actually is practically zero at zero, go up and then go down exponentially. Again, it's a bit more memorable to explain the same thing. These don't contain a lot of new information. It just makes for easier memorization of the same concept. Sometimes you just plainly want to have fun, and this happens. I use making animations a lot. I mean, it's a hobby, but it started as a way of taking my mind off other things. So if you are like me, a lecturer that has to teach students about Lagrangian mechanics, you have a lot of these exercises that are, let's take a point mass that is sliding on a surface and find the equation of motion. How is this going to move and everything? And the point is that the only one that a student can reasonably solve, pen and paper, ever, are always relatively straightforward. They are very simple. Otherwise, the calculation just gets super complicated. But then you are inventing exercise, and they are always a bit similar to each other. And then you just need a break, and then you just go crazy. You don't need to solve it pen and paper because you have a computer. You can ask the computer to do the boring calculation, and you can just solve the same thing of a point sliding on a clean bottle. And it's what's the use of this? Absolutely nothing. There is no use of this. It's just that day I was very frustrated about inventing exercises for students, and I needed 15 minutes to take off my mind of it and make something that I will find funny to look at, and that's the result. This other one is another one that I made just for fun. This is actually visualization of a surprisingly deep theorem. It's probably the math theorem with the strangest name ever. This is known as the Herrible Theorem, that has a very precise formulation, but in a very imprecise term. It essentially tells that if you have a ball and you cover it with hairs and you want to comb them, you are always going to get either a bald spot somewhere or a bunch of hair sticking out somewhere else. There is no way to comb the hair smoothly over all the sphere. There is an infinite number of jokes about the Herrible Theorem. I'm not going to repeat any of them. You can probably imagine all of them by yourself. Okay, now a warning. I've shown you animations I've made of different cases where I think they are useful or just fun. Warning, animations are usually incomprehensible unless you give them context. Unless the person looking at it knows very well what you're talking about, animation are incomprehensible. And this is an example. I dare any of you, unless you're teaching special relativity for electrodynamics in particular, to immediately guess what this is. And that's not really the fault of the animation. It's not your fault either. It's just that there are a lot of these animations are such that you need extra information, and the information is not straight into the animation. This in particular is a relativistic effect. You have a plane wave coming in your direction, in your face, out of the screen, and it's circularly polarized, so the electric field is going round and round and round. And then you're moving sidewise, neither in the direction of the wave, not out of the wave, you're going sidewise at a sensible fraction of the speed of light, increasing. There is here a counter that is telling you how fast you're going. And this is what you're going to see if you see that. First of all, the circular polarization at the beginning everywhere is in synchronous, is going to get out of sync. And then you're going to start to see one side of it that is going to grow a bit bigger and higher frequency. This, if you want, is a kind of Doppler effect, but moving neither in the direction of the wave, not out of the wave, that is the usual Doppler effect, but moving sidewise. You still have a Doppler effect in special relativity, and this is how it looks like. But if I don't tell you, just the animation doesn't tell you anything. It's just a bunch of arrows moving around the screen, nothing else. Now, there is a cheap way of solving it, and it is to put words inside your animation. There are people that are a bit better at it. I'm not particularly good at it. So you can put words there, and while the animation is going on, you change what you're saying, and you add more and more explanations, and so on and so on and so on. It sort of works. I never found it ideal. I have experimented with it a little bit. And again, there are people that are good enough to make it work. I don't like it very much. In this case, technically, the text there tells you everything that you need, but it's not really working very smoothly. This animation is about how a linear planimeter works. If you don't know what a linear planimeter works, what a linear planimeter is an old, extremely ingenious device that allows you to measure the area of things just by moving an object around their perimeter. You start from one point, you make the whole perimeter, you go back to the same point, and the linear planimeter is going to give you the area that you have gone around. It's almost magic how it works. These explain how it works, but the point I want you to get is not how the linear planimeter works, but that you can put text. I don't particularly like it as a solution. Again, some people make it work a bit better than this. Now, to go to the second part of the talk, how do you make an animation? And this is the kind of million-dollar question. Because the point is that there are as many ways, as many ways of making an animation as people making animations. There is nothing that works for everyone. But now I'm going to make a few assumptions. And the assumptions, I'm afraid, are that you are a little bit like me, so I can talk about how it works for me personally. And the first assumption is that you are better at physics, so that you want to make animation about physics, and you know physics, but you're not very good at computer graphics. If you are very good at computer graphics, then there is a whole universe that opens for you, because there are a lot of softwares that you can use to make wonderful stuff. And there are people who do that, and their animation are stunning. I'm not very good at computer graphics. I'm not good at graphics in general. I know a little bit about physics. Therefore, I can make it the boring physicist way. I can, first of all, make all the calculations beforehand. So I want to make an animation about something, then I can do all the calculations. Sometimes I can do everything pen and paper. More often, I ask a computer to do all the simulation for me. So everything is numerical. I'm already doing a lot of numerical simulation for my job. I'm an experimental physicist. Doing small numerical simulation is part of the job description. So I do a lot of them. Then what I do is that I create a lot of frames. I don't create an animation. If you talk with people that do animations professionally, they don't really talk in terms of frames. They think in terms of maybe keyframes. So they have points where they fix what's happening there, and then they interpolate smoothly. They create a nice animation. If you look at animated movies, people animating those stuff, they are really good, but they don't animate each frame. That's the old way of doing things, where people have to physically draw each frame. They don't do that. Wow, they don't do that anymore. They create keyframes where they select exactly what's happening there, and then they sort of continuously interpolate through them. And it works well. It doesn't work very well for me because I'm not very good at animations. So I still do it the old-fashioned way. I just create still frames. And then I get 1,000 frames, and then I just package them. The simplest way of packaging them is a GIF, not entering the word if it's pronounced GIF or GIF. I will pronounce with the Italian phonetics, that is GIF. GIF is just a package of images all together that you cycle through. If your GIF is too big, or if you are a bit better with computer, you can encode everything in an MP4. And these are both very easy to create and very safe to share around with anyone. Now, there is $1 million question here. Which software should I use? And again, there is no standard answer. My best answer there is use whichever software you already know how to use. Don't really start learning anything completely new. Chances are that you already know how to use something. Use that one. And here are a few examples. This magnificent animation is from Dr. James O'Donoghue. I'm not exactly sure how to pronounce Irish surname. I apologize. That his way of working is that he takes astronomical data that are available. He's a planetary scientist, so he knows, like the back of his hand, all this NASA database with all the data. He takes the data and then he just plot them using After Effects. And I asked him why After Effects, and the answer was, I know how to use After Effects. And that's a great answer. He has a great YouTube channel. Go there and check him. Another option, there is a software that a lot of people use, and this animation is from Luca Moroni. And a lot of people use a software called Geogebra. I never used Geogebra. I'm not exactly sure about the details, but it's essentially is a software that allows you to plot stuff. It's essentially a plotting software with computational capabilities in it. A lot of people use it and they swear that is great. I don't have a lot of experience, but I believe them because the results are something like this. In this case is, what would the planet do if there were 3 fixed stars to move around? That is the trajectory around it. Again, he's on Twitter. He has a very nice YouTube channel where he uploads his stuff. Go and check that. Another option is, you might have already seen this animation. I think that is in slide 2 or 3 on any introductory talk about topology. Everybody's using this. 99.9% without giving any credit to the creator, who is Lucas Vieira, that created it with POV rays 14 years ago, something like that. Is an old image, but he's still creating amazing stuff. And he puts everything on Wikipedia. So go to his gallery. He has a large amount of amazing things. Again, why Polarity? I suspect that at the time it was the software, he knew how to use it. He's much better than me at coding, actually. He's actually a proper coder. I'm not. But why Polarity? You could create these with a lot of other softwares. There is no fixed answer. All of them you can create amazing animations if you want. Now, a very small guide about how to make scientific animations. And again, I'm going to make an example. This is an example of an animation that I actually created a couple of weeks ago. So the first step is that you have to choose an argument, and that's very personal. Advice, pick something that you either already know very well or that you're willing to spend time understanding, because you will need to really understand the topic before you're able to make an animation. And example that I've chosen is eigenvectors. Let's talk about eigenvectors. Let's try to make an animation that explains what an eigenvector is. The second point is that you need to visualize in your mind what you want to show. Before you start coding anything, you want to have it in your mind. And that's the hardest part, at least for me. Visualize and think what's going to happen. And my mental process there was, I want an animation that explains what an eigenvector is. And I'm going to go 2D. Why 2D? Well, because 2D is easier to read. You can make great 3D animation. They are invariably harder to digest for the audience, especially when the animation is not the point. The animation is a tool to explain something. Now, if I have to plot eigenvectors in 2D, I know my algebra, and I know that I have to fix myself with 2x2 matrices, and in particular 2x2 real and symmetric matrices. Otherwise, if I go higher dimension than that, I need more dimensions to plot. And that fix, this is a constraint that you have to work with because you have made choices. Choice eigenvector, choice number 2, I want a 2D plot. So these are my constraints now. And now what I can do with these constraints? Well, 2x2 matrices, again, I know my algebra, has a nice interpretation that can be interpreted as stretching the axis and then shearing the plane. So the first thing that you want to do, if you want to make this, you create a grid of points that is the starting point. And then, okay, any 2x2 matrix, what it's going to do is going to stretch vertically, stretch horizontally, sorry, and then shear the whole thing. So the final result is going to be this one. Now, these two are by themselves not very good. This is not an animation. So what I can do is that I can say, okay, a matrix is going to jump directly from this to this, but I can make a linear interpolation. I can get intermediate frames by saying, okay, I'm going from this set of points, from this set of point, and I move each point linearly in a straight line at a constant speed from the point where they started to the point where they arrive. Okay, now I have a bunch of frames. I package them as a GIF. I put it there, and that's what I get. And that's a very good starting point. Because what I'm still missing is to put there the eigenvectors. Now, what are the eigenvectors? What is the goal of this? Well, the eigenvectors are the two directions where a point sitting on this line will not be stretched, sheared, and everything. It's just going to slide on the line and do nothing else. This is what an eigenvector is. And the eigenvector of this 2x2 matrix is just those two lines. Now, if you are using this for teaching, like I do, I make this for a lecture, you can use this to also explain that, look, it's 2x2 real and symmetric, so these two lines happen to be orthogonal. It just means that if instead of having my x and y axis, if I rotate my head and I look using the red lines as my axis, there is no shearing anymore. There is only stretching. all points are moving either parallel to one of the two lines, two red lines, and nothing else. There is just stretching if you go there. Now, as an animation, this is fine. There is a couple more things you can do. Well, first of all, you can make the animation cyclic, so you don't have that jarring stop when it finishes. You can just make go and then go back. It's even a bit better if you make a bit of pause at the two extreme. So it goes, stops, and then go back, go back, stop, and that's it, and it goes like that. This is a perfectly fine animation. It works. It doesn't take a lot of time to code. It doesn't take a lot of skills to code. The only real skill to make this is that you need the idea of what you want to show, and you need to think a bit about how to show it. Now, if you wanted to make it a bit better, there is another thing you can do, and this is something that we can learn from people doing proper animations. And this is what is known as an easing function. An easing function is a function that instead of moving linearly in time, so things just move and then they abruptly stop at the end, you can make things smooth. You can say that it starts slowly, then speeds up, and then goes slowly again until it stops. So it do something like this. This is actually my favorite easing function. You start from still, you start moving, you go, and then you whoop, you slow down again. There are many easing functions that you might want to use. This is my favorite for this kind of things, but there are other depending on what is your goal, what is the animation showing. I had a lot of fun in other cases using this one when something just go and arrive at the end and make boing, and it just gives the impression that you're moving fast, and then you stop suddenly. It helps selling the animation if you want. Anyway, these are also made in Geogebra by Professor Vincent Pantaloni. He do a lot of stuff in Geogebra. Go and watch that. Seriously, he's very good. So, is the difference huge? So now I'm easing the animation. No, the difference is not huge, but it's subtle and important. It's one of those things that will make the difference between people saying, oh, this is a nice animation, and people feeling that is a nice animation. These kind of things are mostly subconscious, but they are important. So, going to the end, don't worry. I don't have a lot going on still. So, before the conclusion, I happen to have a couple of pre-conclusion. And one of them is I'm going to preempt a possible question. That is, what about interactivity? Interactivity is great because especially if you want to use it as a tool for making people understand and learn, interactivity is seriously great when it's done well. Interactivity does wrong is terrible, is much worse than anything else you can do, which means that interactivity is hard. You cannot make an interactivity that is so-and-so. You can make a figure that is so-and-so, and it's still fine. In animation that is so-and-so, it's not great, but okay, you can still do. Interactivity that is not great is going to just make people extremely annoyed. Furthermore, a still image is something that is very easy to convey, apart from print page, but all of your digital device can read a JPEG or a PNG image, easy. If you want an animation, we also have standards. A GIF or an MP4 are readable by everyone. Everybody that has a screen and a computational device, be it the cheapest smartphone on the market, the cheapest computer available, they are going to be able to see that. Interactivity is more complicated because there is no standard out there. There are a lot of ways that you can make interactivity, but it's not standard. How are you going to make it? There are different approach. People are still trying stuff out. We're not there. We are going to get there. I'm absolutely sure about it. Give it a few years, and people will find a good way of making interactivity about these things. We are still not exactly there. Another pre-conclusion, and this is a bit of a little secret that people don't seem to realize how many times I start an animation and think, okay, I would really like to show this, and yeah, I think I get it. Then I go there and I start coding, and usually my codes are never very big. It's very difficult that they are more than 20 lines of code to make the whole thing. I start coding and realize that I don't really either remember or know that bit of physics as well as I thought I did. So what I need to do to make an animation is that I need to go back and restudy the whole topic once again. This is an example of an animation I made about Lagrangian points. If you know a bit of astronomy, if you have two bodies that are rotating around each other, there are 5 points where all the forces cancel exactly. These 5 points are points where if you are sitting exactly there, you feel no force there. So they are very good points where to be if you are a telescope, for instance. Now, 3 of them are unstable, so you see these gray dots there that are placed very close but not exactly on the Lagrangian point. They just, after a short while, they just start flying around and start orbiting in a complicated way. 2 more that are labeled there as L4 and L5 are actually stable. So if you are sitting there, you're just going to stay there. You're not going to stay there sitting still. You're just orbiting around the Lagrangian point. Still, Lagrangian points are great for telescope, and people are using them, I think, especially L1 and L3 there, that are the one between us and the sun, and L3 is the one on the other side, is a very good point where to put a telescope. Because it's unstable, but still it doesn't need a lot of corrections to be there. Okay, stop at the digression. My main point is that I started this fully convinced I could do it because I know mechanics, and this is not particularly difficult mechanics. And then it took me a week of studying planetary dynamics to finally understand exactly how to code this. It took me time. I had to ask help from other people that are better than me at planetary dynamics. In the end, it's not super difficult, but it took me time to get there. So if you don't already know very well the topic, chances are that you will have to spend time studying it if you want to make an animation. Okay, conclusion for real. These are the real conclusions. And let's phrase in terms of questions. Should I try to make scientific animations? And the answer is, well, it's up to you. It's not mandatory. And beware, it's a huge time sink, especially if you are having fun doing that. But if you are doing any kind of science yourself, or if chances are that you have already 99% of what you need is already sitting on your computer, because you have already done it. You have already done the calculation, the simulation, you have already plotted the thing. You just need to simplify things out a bit and then make an animation out of it. And the usual thing that you might say or think inside you is, yeah, I'm not really good at this stuff. My animation won't be any good, so why bother? And I'm not very good at this stuff either. If you look at my animation, they are always on the very simple side because I'm not particularly good at this kind of stuff. And my advice, if you want to give it a try, is that start simple. Now, simple is difficult. Don't get me wrong. Simple means that you don't have to be good at art. Simple is difficult because you have to take your idea and start throwing away stuff that at the beginning looks like a very good idea and remain with just the core of it. And you will find that animating that core is easy. You probably already know how to do it. And once you try it once, you will surprise yourself about, one, how easy the technical part was, and how good your animation is, and how many people will actually like it. So Thank you very much for your attention. I spoke for almost 1 hour straight without any pause. So now we'll be very happy about any question. And if by any chance I manage to inspire any of you to make a scientific animation, send me your animations. I will be extremely happy to see them. So thank you very much for your attentions.
Thank you, Jacopo. Professor Bertolotti, thank you. Let's thank the speaker for this brilliant talk. So, as I see, okay, so the first question is from Fabrice Lassie. As an experimentalist, have you tried animations with real-life objects, physical measurements?
Okay, animation with real-life object. I assume that you're talking about step 1 animation, where you take a photo of your things, then move things, and then stop again, and things like that. Those are great, but they require a huge amount of work, to be fully honest. That is something that it's a lot more work than what I'm talking about here. If it takes me an hour or two to make a standard animation, once I know all the physics that I need to know to make it, making something with a real object moving is going to take a lot more. What I'm thinking about doing, because as many lecturers around the world, this year I became very good at editing video because I have to edit my own lectures. Because all the lectures are online, so I have to edit myself a lot. Last summer, I knew nothing about video editing, and if you will ask me about do video editing, I will laugh in your face. Now I have edited a total of 30-hour plus of lecture for myself, and I'm going to have to edit another 10 something in the next few weeks. So now I know how to edit video, which therefore I'm starting to think about recording videos with my phone about things moving in the lab or something like that, and then edit them to create an overall animation. That might work, but frankly, if you were to ask me 1 year ago about doing that, I will have never considered that possible. Now I learned how to use a video editing software out of necessity for my lectures. So again, if you know how to use a video editing software, do that by all means. Don't start learning how to use a video editing software just because of that. Start with what you already know. That's probably plenty. But most lecturers by now probably know very well how to edit video for lectures, so that might be a good starting point.
Okay, so the next question from Maurizio Vannoni, who's asking how much time you needed the first time and how much do you need now on average for each animation?
Okay, there are two separate parts of making an animation. The first part is to be sure that I actually understand what I'm animating. Well, three parts. Understanding what I am animating, understanding how to code what I want to animate, and actually coding the animation. The first part can take anything between seconds, because I already know very well what I'm doing, to weeks or months, or there is no upper limit. I have a few that are in the to-do list that I just realized I don't understand the physics well enough. They're just sitting there. And I'm not sure we'll ever have the time to actually learn what I need to learn. So this is the really time-consuming part. Learning, understanding how to code it is usually not super difficult, but it has happened that I got stuck because I needed something to make my vision through the. I'm not really sure how to make it. I have one in the to-do list about how rainbows are created that I never came up to do. I know very well the physics there. That's not the problem. But I'm not exactly sure how to plot the things that I would like to plot there. And then I'm stuck there. And that is really going to be dependent about how good you are at coding. I'm not very good at coding, so sometimes I just get stuck. And by stuck, I means I can probably solve this if I will be willing to spend a few hours on learning how to make that. And I don't have that kind of time, so I just put things in the to-do list and they are going to be waiting for time. Once the first two steps are done, how much time does it take to take out the animation? Usually minutes, to be honest. There are a few cases where I just have to run the simulation and let the simulation run for hours, and then I just get the result of the animation, I plot it, and I save it as a GIF. And then the simulation can take ages. But frankly, the last part, the part of really making the animation, is very short. It doesn't take me a lot of time. It's the first two pieces that are usually the long ones. And honestly, the first bit, be sure that you understand the physics, is the part where I usually don't tell people how much time I have spent relearning the physics, because I'm a bit ashamed of it. You go down, you just try to plot things and they don't work. And then you try to find out why they don't work. And the answer is usually, no, you're writing things down wrongly because you just thought you understood the physics. You didn't really. So that's actually a very good excuse for me. I nowadays use these mostly as an excuse to either refresh or learn new bits of physics. I've learned more new physics by doing these animations than by reading scientific papers in the last couple of years, to be fully honest.
Thank you, Jacopo. And by the way, thank you for a nice idea on semester project for our students to simulate formation of rainbows. Okay, so there is actually one question from our student. What is the animation you're most proud of, and how long did it take to complete? But okay, yeah.
What's the animation I'm most proud of? Okay, okay. The animation I'm most proud of is by far not my best animation, nor is the animation that people like the most. The animation I'm most proud of is an animation I made. Was actually almost at the very beginning. I think it's my overall fourth or fifth animation ever, and it is about the Fermi-Pasta-Ulam-Singu problem. You might have heard of it. If you have a chain of masses with spring between them, and you excite them, I mean, each eigenmodes will just oscillate as its own eigenmodes. So you might have oscillations that are complicated, but it's not really complicated. Each eigenmode is just an eigenmode. And your thing is going to be periodic. Now, if you make this nonlinear, you can easily get into the chaotic regime. What Fermi, Pasta-Ulam, and Singu found out is that actually even this can be periodic, meaning that it doesn't matter what you start with, all these complex and chaotic things, completely nonlinear, you start creating solitons and all these kind of things. Sooner or later, you will go back to exactly the initial condition. And this was a big deal in nonlinear physics. And there is still people nowadays studying these kind of problems. It's a big thing. Why am I proud of this? Because, again, first few animation, I started this saying, oh, yeah, it's just a bunch of masses with a nonlinear term added. It will be an easy one to do. It took me weeks to learn the physics of the Fermi-Pasta-Ulam-Singu problem. And I'm really proud because I was super happy about it. It was the first time in my path in doing animation where I actually encountered something that I thought it would be easy. And actually I realized I did not understand the physics. And I just went down and I understood the physics. And I felt good at the end, to be fully honest. I felt that I properly understood, not just because I could go through a book and just skip through the question and say, yeah, it works. Okay, fine. That's what I did before. I already knew about it. I already read it in textbook, and I just skimmed through the thing like you will often do. This time around, I really had to understand it properly. And once I did it, I realized that it was since I was a student that I didn't do that properly. As a student, when you prepare an exam, you go through every single detail. But afterward, you never have the time to do that. You never have a good enough reason to really go through every single minute step in the thing. You sort of trust that things work. And that was my eureka moment. I realized that one, I could still do it. I could still really properly learn new physics. And two, that was actually the reason why I like doing science. I don't like doing science because I like being a professor or because I like to publish. I have to do this kind of things. I like science because I like learning stuff. I like the process of going through things and at the final point to be able to say, yeah, I really get it. That's why I like science. And this is nowadays is helping me renewing constantly my love for science.
Thank you, Jacopo. I think it's especially useful for students. Well, there is a part of it in convincing others, right? When you want to demonstrate some effect. But then on top of that, the first part is to actually understand it yourself. And well, sometimes you can use simulations to see the patterns that emerge from there. So you first simulate it, and then suddenly you understand something that you didn't understand before. So there are actually many questions. I wonder. So we are not really limited with time, I hope.
Well, at a certain point, my son is going to start knocking at the door, but apart from that.
Okay, and until that, I'll go on. So there is a question from Farah Christina. Can you mention some of your favorite softwares? Practical question.
Okay, I do everything with Mathematica. And the only good reason is that as a PhD student, I had to learn how to use Mathematica for reasons. I liked it. I kept using it. And it works well enough. It's not ideal for this kind of things, but it works pretty well. And I never had the time to learn anything else. So I used Mathematica. And I go back to my previous point. Please use the software that you already know how to use. That's probably good enough. I know people that use Python a lot. I never had the time to learn Python, but you can do exactly the same stuff in Python if you want. MATLAB is the same. If you know MATLAB, you can do exactly the same thing. I'm not going to say that you can do the same thing in C. You can. I'm not going to advise you to, because unless you're very good at programming in C, it's going to be extremely long and tiring to rewrite everything from scratch. The lower level of the programming that you go, the longer it's going to take you to do things. But if you are good at C, by all means, just go for it. And as I showed, there are a lot of people use GeoGebra. I don't have any experience using it. I've never made anything with it, but really a lot of people swear that it's great. So probably they are right. I promised myself that one day I will learn how to use a proper 3D software, something like Polarity or Blender or something like that, just to do the simulation and then import the simulation in the proper 3D rendering software, so to make the final animation look prettier. But so far, I never managed to find the time to do that.
Okay, that, by the way, answers another question. Do you use Python when you code? So there is a couple of questions. On the interactivity part, can you talk more about the interactivity and what do you mean by the interactivity done right and wrong?
Okay. Let's think about how you can make interactivity. The easy way of making interactivity is to have essentially small software that do the simulation, then you have slider to move around. And you can say, for instance, I don't know, I'm an optics guy. You can have a code that show you what is the wavefront when you're focusing a beam, and you might be willing to have sliders that change the focal length, the aperture of your lens, the wavelength, and you might change this, and in real time you change the image. That's interactivity. It works. It's my experience with this is that usually works very well with people that already have a very good idea about what you are talking about. So if they already sort of understand, for instance, how light is focused, then you give them something like this, and it's great because they can explore and get a feeling. It's a bit like being in the lab and doing it for real, but without a lab and without the risk of burning anything with a laser. So it works. It has a problem in, okay, which software are you going to use to do that? Because chances are that the person that needs to go there and slide things needs to have the same software as you did, which of course make life complicated. Again, I use Mathematica. I know very well how I could put sliders there, but the only way for you to actually go there and slide things is to either also have Mathematica, which is an expensive piece of software, or to go download the visualizer for Mathematica. They exist. You can, it's free. You can download the visualizer and then open my interactive object with the visualizer, which of course is a barrier to entrance because you cannot just do that. You need an intermediate step of downloading the visualizer for the things that I'm doing. And the next person is going to use something different. And you have, they are going to be using Java. And then you have to go download the Java runtime engine, and then in your browser run the Java runtime engine and get the interactive thing. It's possible, but it's not ideal. There are people that are able to code everything in HTML5, which sort of solve the problem, meaning that everybody can open an HTML5 file as long as they have a browser. And nowadays, everybody who's anyway going to look at an animation or interact with something is probably going to have a browser. Problem with HTML5 is that it's not meant for that, so it's a bit clunky, and it's not meant to run a simulation in the background. So it's very nice if you already know what the solution is going to be and you can predict everything and just plot it. If you have to run very quickly in a simulation in the background to show what's happening, HTML5 is not ideal. Then you need, it's a problem on your side as people doing the interactive one to make the whole thing working. Now, this is the easy way of doing interactivity. The way that probably people will really like to have these things really interactive is to have something that looks a lot like a video game. That is, if you want, the holy grail. If I could teach electrodynamics to my students inside an environment that is essentially Minecraft, everyone's life will be much easier. My life, because finally students will pay attention to the lecture, and students' life because we'll actually have fun during my lectures. It's a win-win situation. Problem, who's going to code that? Seriously. It's very difficult to make something that is both interesting to interact with and actually teach you something. It's very easy, well, not very easy, but people making video games are very good at making something that is fun to interact with, but it doesn't really teach you anything. At a certain point, people created some physics demo inside Portal. You might remember the video game. Portal 2 had a level editor, and people create physics puzzle that will teach you about classical mechanics inside Portal 2. It was great. I don't think that many people ever heard about it because, well, one, you needed to buy Portal 2 in order to be able to run it. You needed a computer powerful enough at the time to run Portal 2, which it was not a given. And after that, you needed to know where to go to search for it, install it as a mod, and then run it. Yeah, okay. The fact that not every possible student have used it is testament to the fact that it was a good idea, but it was not a perfect idea. And this was made well. If I try to make something similar with my skill, it will be horrible. Nobody will have any fun with it. It will probably be clunky. It will be move this object there and see the things have, it will be terrible. You don't want that, seriously. So that's what I mean about interactivity done wrong. And people have tried. You can go around the internet and find software that are meant to teach you about this and that, about fluid dynamics and things like that. There is always a huge amount of goodwill behind the people doing them, a huge amount of work, and 9 out of 10, they are terrible. We are still not there with interactivity, to be fully honest.
Okay, thank you. So there is, well, a kind of specific question about the Mark II donut animation, but I'm not sure if you want to answer this question or you want to refer to some other talk.
Sorry, which animation?
Mark II donut.
Okay, it's not my animation, but I don't know how much I can tell about it, but yeah, okay, let's talk about this one. What is the question?
It's just like that. Can you explain the Mark II donut animation? Like what the purpose is?
Okay,
and
it's about topology. If you topology is a branch of math that studies the properties of objects, mathematical objects, very often that are invariant whenever you stretch, deform things without punching holes or breaking things apart. In topology, essentially a mug and a donut are the same object because they are characterized by having one hole. Anything that have exactly one hole is in the same homotopy class, if you want. That's the thing that usually this animation is meant to explain. You are explaining what a homotopy class is, that is all objects with 0 hole. So everything is essentially the same as a ball. Every object with 2 holes, and everything is essentially a donut. Every object with 2 holes, and I don't know what's the English name for an object with 2 holes, and I seriously doubt that there is an English name for object with 3
pretzel,
or more
probably.
holes. Pretzel like... have 3 holes, 4.
Aha, right.
3 or 4. It depends a bit how you fold. I think 3. Okay. Yeah, but I mean, a pretzel has 3 holes and is in the same homotopy class with anything else with 3 holes. The nice things about topology is that you can actually say a lot about all objects in the same homotopy class, which are, as you can imagine, a lot of very different objects. And this animation is wherever you want to explain this, the fact that objects with 1 hole are in the same homotopy class.
Right. So there's another question from Fabrice Lassie. Do you think some things are better left in the abstract with no attempt at visualizing them? Like examples such as entanglement, wave-particle duality, and so on.
I think that there is stuff that is very hard to visualize. And if you do the visualization wrong, you might do more harm than good. Entanglement is a very good example. Can you visualize entanglement? I think so. But 99% of the visualization I have seen about entanglement are terrible, genuinely. And not terrible because they're bad visualization. They are terrible because they are terrible at physics. They are wrong. They show the wrong thing. They always try to visualize entanglement as in terms of classical mechanics, and that's effectively wrong. There is something that is actually called classical entanglement, but it's a bit of a different animal. So it's probably easier to visualize the classical entanglement, but it's related to the quantum entanglement, but it's not the same thing. And people have the problem that they tend to go a bit too much into simplification with this kind of thing. Particle wave duality, I have a strong opinion that the wave particle duality is an absolutely wrong, fake problem that just stems from the fact that from the history of quantum mechanics, it's not a real problem, but that's just me. But there are other things. Let's say, I think that everything will benefit from visualization. There are topics that are very hard to visualize. And don't ask me how to visualize entanglement. I don't know. If I knew, I will have already made a visualization about entanglement. But if anybody find a nice way to visualize entanglement, they by any means they should do that. Visualize entanglement if you can. It's just not easy to do. That's my only point.
The best visualization of entanglement that I've heard of is a pair of socks, and once you put one on your right leg, the other one automatically becomes the left one. But it's just a joke.
More a visualization about spontaneous symmetry breaking, if you want.
Well, okay, you can probably.
Both of them are can be either left or right, depending on choice. But then you break the symmetry.
Yeah.
You get a spontaneous symmetry breaking of the system. I will not call that a visualization of entanglement. It's more about spontaneous symmetry breaking.
You are actually right. Yeah. Okay. So another question from Lucas. Hi, Jacopo. Thank you for the great talk. And
Lucas, I suspect that is the guy that created this.
Is it?
Yeah, I suspect. Okay. Hi, Lucas. Okay.
I see. Well, actually, it seems to be the case, right? Well, he can confirm it in chat. So the question is, what sort of interesting feedback have you gotten from students and other teachers?
Okay, students never feedback about it. Students seems to not see, well, I think that students, when they see them in the lecture, they appreciate, meaning that it helps them understanding, but I don't think that they appreciate the amount of work that comes to create them. So I actually never got any feedback from any student about it. Neither to tell me to get rid of them, neither to tell me that they liked them or that they were useful, nothing. So I had no feedback whatsoever from students. From other teachers, much better feedback, because one of the best things that I can hear about this is when somebody say, oh, this is great, I'm going to use this for my lectures. And I know several that actually has used several of my animations in their lecture, and this makes me incredibly happy, because it means that they think that they will help their students, which means that I made a good animation, if you want. The animation was clear. It's complete success in that respect. So I have several people that mostly people on Twitter that I regularly get messages or sometimes email. It's not difficult to find my email around, asking, can I use this for my lecture? My answer is invariably, yes, please do. I'm super happy if you do. Any of my animations are free for you to use in your lectures. And actually, if you need something for your lecture and you think that you will like the same animation but slightly different, let me know. I will be happy to modify my animation just to suit your lecture if you need it. I'm super happy whenever anyone uses them for lectures.
And yeah, by the way, Lucas confirmed his identity. Another question. Okay, so I'm not sure if it's clear, but well, you tell us, how much should you simplify? For example, how do you decide whether to draw electron as a particle, wave, cloud?
It depends a lot what is the goal of the animation. I mean, an animation, again, doesn't exist in a vacuum. An animation is there because you, small guide. The first point is to choose an argument. What do I want to show? If I want to show tunneling, the first animation I showed you, let me go back to the very beginning. If I want to show tunneling, what should I show there? What is, if I show my particle as a ball, it's not going to be very effective. The only thing is going to happen is that there is going to be a ball arriving to the thing, reflecting back, and the ball may be a bit transparent that passed through to signify that it was transmitted with a small probability. Or someone might make it a bit smaller. Is that a good animation? Maybe. You can find a lot of animations like that. I don't like it. So I have to plot something else. What can you plot of an electron otherwise? Sorry. You might plot the wave function, but the wave function is complex. So you have to make a choice. Do you plot the real part of the wave function? Actually, I have an animation exactly like this with the real part of the wave function plotted, because I think it's instructive to have both. I couldn't show all of them, but I have that. But maybe if instead of the real part I show the modulus square, therefore the probability, that maybe is more instructive. And again, it depends what you want to show. In this case, I'm showing the probability, modulus square of the wave function, which I find instructive because there are all those fringes. You don't really get those fringes if you show the real part. Those fringes appear because of the interference when you make the modulus square of things. And it shows that there are moments where there are points where you cannot find the electron. The probability go very much down to zero. It's just for a transient. It's just there is a moment where at this point, there is no way that you will find the electrons there. It's instructive. And again, it doesn't come from the static figure or from the equation. It's inside the equation. I'm doing here nothing else than plotting the equation if you want. And spending 3 weeks learning how to properly integrate Schrödinger equation without getting drowned in numerical artifacts. That's another things that you learn making this kind of animations. Because the standard way of integrating differential equation don't work very well. So there is a specific class of numerical integration techniques specific to the Schrödinger equation. So, but apart from that, I'm just plotting the Schrödinger equation, nothing else. So how did I choose to plot the probability? Well, it's just a thought. I'm just thinking, what do I want to convey? I'm using this animation to explain something. That's my goal. If my goal was something different, if my goal was to make something that is an artistic impression, I would probably not plot probability. Probability go very bad for artistic impression. I don't know what I will do for an artistic impression because I'm very bad as an artist. But I'm sure that somebody who has an artistic soul will be able to come up with something different. I don't want to show, I don't want to convey this. I don't want to start talking about the interference effect, about the fact that the probability is continuous at the interface of the barrier and everything like that. If I want to do something artistic, I don't care about that. I care about something else. I care about creating a feeling. So I might show something different. And maybe it will be a ball. I don't know. Ask somebody with more artistic skills. Maybe they will make a great animation about this. I don't know.
Thank you, Jacopo. And well, we are actually out of questions. There are some comments on the other hand. And thanks thanks to the speaker from Devesh Chandra. And I think that we can, also thank the speaker once again and join. So thanks, Jacopo. Well, it's kind of awkward, but I'm sure that.
Thank you very much for inviting me, and thank you for everyone who listened to the end of this.
Everyone who is staying right now, I suppose, is well, joining me. And the final comment is that well, actually, we would like to advertise your Twitter account. Although, could you actually tell us its name?
J_Bertolotti is my Twitter account. I post post my animation mostly there with a small amount of text that explain what's happening. Why? Just because I started there and people appreciate it, so I kept doing it. I actually, all the ones that I think are worthwhile, I also upload them on the Wikipedia and put them in the public domain so that everybody can use them. So if you decide that you want to use one of my animations, chances are that you can just go on Wikipedia and Google for my name and find everything that I have uploaded on Wikimedia Commons, where all the images are stored and everything. And they are all on the public domain, so feel free to use them. Otherwise, I'm not on many other social media apart from Twitter. But yeah, if you like them, come and say hi. It's always appreciated.
And well, there is a request. Probably you'd want to also tweet the link to this to this talk on YouTube once it appears on YouTube.
Once you tell me where is the what is the YouTube link, I will surely link it on put the link on Twitter. If nothing else, for bragging rights.
Right. Well, we'll certainly do that. All right. So at this point, I would like to thank the audience for staying and for staying with us and listening, and probably well, invite you for to the upcoming meeting as well. Fabrice, are you there to maybe tell us where, at least when it is going to happen?
Yes, I'm there, of course. You see, I was very comfortable, like looking at this like a movie. Next talk will be 30th of March. It will be given by our colleague.
It's actually hard to hear you.
Is it better now?
Yes.
Yeah. Okay, so the next talk will be given by Juan Camilo Lopez Carreño, 30th of March, and it will be on on what Jacopo commented is the mystification of physics. It will be on the wave particle duality. So you can follow us on our own Twitter account to make sure of the date and where it will be. So thanks again, indeed, everybody. Thanks, Jacopo. It was fantastic, very inspiring. We'll try to make some of these animations and follow you in your tracks. Thanks, everybody, and see you soon. Ciao, ciao.
Thank you very much.
Bye-bye.